Okay, let's get started. Thank you all for joining. It's really a great turnout, and to be honest, I didn't know what to expect for this quite strictly an infrastructural topic on a developer conference. Whilst on the other end, I think, and probably this is something that a lot of you have asked yourself. Why am I getting great disk performance at one time, and why is it all of a sudden slow at another time? And this talk is aimed on providing you to show you examples of why it could be different, but more importantly, on Linux, on how to measure it to understand why it's actually happening. And hopefully you can also then understand some common pitfalls or realize why these figures were off. And that is the aim of this presentation. And I think it's vitally important. I'm Frits Hoogland. I'm Dutch. I only had 1 year of French at school, which is not enough to deliver a presentation. So sorry about that. I'm doing it in English. Hopefully you forgive me for that. I work for Gigabyte, and we build and have a distributed database where Frank told about yesterday, and that is also worth checking out because we allow a database to exist over multiple availability zones in a cloud, and one of them can be dead and everything will still continue, which I think is a major advantage over common databases. But today's topic is memory usage and disk performance, and hopefully at the end you will see that these two have a really important relationship. And the point is, you need to understand some of the details. There is no way around that. In order to understand what's going on, you need to understand some of the details and where to look for. And the major point of this slide, what I want to say with this slide is, it is not common and not understandable for a lot of people that actually your memory usage and the way you use memory and the amount of memory which is in use is really important to how disk I/O performance behaves for an application. And even if it's not a database, lots of applications store data or do other things with a disk, and you want it to be performant, or at least to be predictable performance, so that it's not fluctuating all the time. Okay, first topic is regular disk I/O. Any regular disk I/O is performed buffered. There is another option, which is to perform it using ODirect, but ODirect is a flag which explicitly needs to be set by the application, and ODirect means that the I/O is done directly to the disk system, and it completely bypasses the page cache, the cache of the operating system. Some applications, for example, like the Oracle database, if explicitly set, use this because they want to cache everything and they want you to build to set a really big cache, and then having another cache sitting in front of it is simply not a good idea, and therefore Oracle allows you and advises you to set ODirect. If you now are a bit confused and think, how do I find out if my application is doing ODirect or not? If you do not know if it's doing ODirect, then it's probably performing buffered I/O. For example, the Postgres database, which is increasingly more popular, I should say, and we also use it, the Postgres database uses buffered I/O and explicitly asks you to set a small cache for the database itself, and it tries to take advantage of the operating system doing the caching for it. And that has some implications if you start using memory, which again, I think is an important topic to actually understand that. So Linux, and this is a topic which also still confuses me. Linux does not have a dedicated area which you define and set as with hard minimum and maximum limits in the operating system. Any memory which is not actively in use can potentially be used as buffers. And that is a really interesting concept, because that means that there are no guarantees. Or, if you look at it from the other side, you have to be careful with your allocations of your applications to not take excessive amounts of memory in order to leave memory for cached IOs to be performed. And the meat of this presentation is showing you, using a tool called FIO, undoing buffer disk IOs and showing you what the difference can be. And in my opinion, these differences can be really, really staggering. These can be really, really huge. But the important part is, the second point is, if you do buffered IO, it needs a little bit of memory. So for any IO you do in your application, or also if you just copy a file on the operating system, you're doing it buffered, unless explicitly configured not to. And then it needs a little bit of memory from the operating system to hold the data. If memory is scarce, so if your application is set to take a lot of memory, and certain a lot of applications actually are set to have a really huge limit. If applications take memory, so memory is almost not available, what will happen is a buffered IO still needs that memory, but it will be released immediately after. That is also true for writes, but writes are special, and I will get back to that, because writes have special properties, which are kind of obvious, but I will explain that later. The important part here is that if you do IOs, these compete with regular memory usage. And this is not something that is being said a lot, but that is what you need to realize. If you're doing IO, you need some memory. Even if it's only for a short amount of time, you need some memory. Even if you read it, if you have an application and you say, but I don't really need it, because what I do is I fetch some data and I store it in my application, so why does it need to be stored there? That's the way buffered IO works. And the operating system is trying to be helpful to put it there so you can reuse it for another time. And that reuse is what I will show with a demo, which you can also, and maybe even if you are interested in this, should repeat. But it will be stored there. And if memory is at a premium, if your application has already allocated most of the memory because you think, I've got, for example, a system of 2 gigabytes, so I can create a heap for my application of 2 gigabytes. No, not really, because now if you're doing your IO, there is a tiny amount of memory left, and it still needs to be there, allocated first. Then your application will take it, and it needs to be deallocated. And I think you can now understand where the topic of IO and memory comes from. If that memory is at a premium, then fetching IOs from that memory will be getting hard, and will need the operating system to do things for you to facilitate that memory. So, but where does that go? That is the upper topic, the topic of this slide. Where do these buffers go? Because I didn't really say that. Well, Linux provides you in the proc file system. The proc file system is a meta file system which allows you to see and set things in the kernel. And proc meminfo will tell you details about how memory is used by the operating system. It is a messy gathering of memory-related statistics, and I think that is the best description that you can have, because you cannot add up all the values. Some of the values come back in other values. Some of the values are not even in kilobytes, I think is the default unit size. Some of them are in pages, etc., etc. It is useful, it has a lot of details, but it's messy. You need to understand what you need to pick. And like I said, some of the named values in there contain memory, which is also in other values. So if you really force me, where does this cached memory go? Well, it goes in cached, kind of obvious, dirty for writes, and mapped, perhaps. But mapped can also contain other things. Cached can also contain other things. So, but what am I saying now? Because I stand here trying to make something clear, and by saying that it's not really, that it's everywhere a bit, but not really anywhere really concrete, I'm not making it understandable. But probably the best way of explaining it is you shouldn't look at these statistics for that purpose. What you should do is look at a statistic which is called memory available. And memory available is the one to look for. What I see a lot is that people look at mem-free, and mem-free has this natural thing of saying, okay, but that's the free memory I want to look for. Well, no, this is not the mem-free you're looking for. Mem-free is not available memory. This is actually kind of special. Mem-free is explicitly freed memory for reuse by processors if they allocate memory. And these this memory is explicitly made free and needed, but it's kept at a minimum by Linux, because all the other pages which you read, which you don't use anymore, are kept for the sake of being reused. And if it all would be freed as truly free memory, then you can't reuse it and you don't have a cache. So that doesn't make sense. But the important part for this slide is, don't look at mem-free. It is useful to look at mem-free for different topics. For example, if your applications need to allocate memory, they need free memory. And there is a whole world underneath that, which is more a memory topic, and I'm actually working on a memory topic for that to explain how that works, because that is also something which most of the time works okay, but if you do excessive things, then it might need a bit of understanding. And I've got a link on this page, a web link in which I wrote about how that works. It is kind of interesting, but the important part is, don't look at mem-free. So look at mem-available. And mem-available is a relatively new statistic in the Linux kernel, which is a kernel estimation of the amount of memory you can get from the operating system without requiring swapping. And many of the other topics in meminfo are useful, but for the purpose and for the sake of understanding how much memory you can use and is usable, look at memory available. And this is important because the buffering can do miracles for you. And hopefully I'll be able to show you that by doing testing. This is my system on which I test, and it's a relatively small system. It's in Amazon. It's an Amazon EC2. It's a C5 large system. And here's one thing which I see quite consistently going wrong, and that is, if you're using a cloud virtual machine, the cloud vendor put limits on the system for the sake of dividing the resources between all the virtual machines in order to give everyone what they paid for. So you don't have unlimited resources. These are really limited. In fact, I wrote another blog post in which I explained that in the old days of rotating disks, when RAID sets didn't exist, it was really hard to very well tune an application doing disk I/O, because you needed to understand the rotating properties, needed to divide it very well. Then came RAID sets, and with RAID sets it allows you to create virtual bigger disks, which made it easy because you had more I/Os. Then came SANs, and with SANs you had bigger caches, and it made it even better. And then came NVMe and SSDs and even writable memory, which made it so disk I/O problems at that point were nearly gone. And then came cloud, and cloud said, oh, by the way, you have 125 megabytes per second, which I have on this disk, which is actually the same limit I had on a 15 RPM K rotating disk. So in that sense, we are back to square one now with clouds, by having disks which have really low limits again, and we really have to think about it. But and it's not only disks which are limited, it's also your virtual machine. Smaller virtual machines have bursting limits, and that is why I say 20,000, 4,000 IOs per second. The burst limit is 20,000 IOs per second of my C5 large virtual machine. And if you read the documentation for this type of system, I'm allowed 30 minutes of 20,000 IOs per second on this system, and after that, the rest of the 24 hours are limited to 4,000. That phenomenon is called bursting, and um, and this is important because a lot of people don't realize that they have a limit on both the virtual machine and on the disk. So that is a really important takeaway. If you are running into disk limits, very carefully look at them. Look at my last two lines. I'm not saying that cloud vendors are lying, but I will say that they make it not that obvious that you have these limits. You really need to understand what you're looking for to find these limits. The host limits are not obvious to me, and a lot of people miss them. People understand that disks have limits, so if you buy a small disk, you have a small amount of IOs, and if you buy a disk with a lot of storage, you have a lot of IOs. Anyways, my IOs per second limit is 3000, and my megabytes per second limit is 125, and that is that can be reduced by bursting, but I'm not running into bursting limits, as you will see. And what I'm going to do is I'm going to read a file using FIO for 2 gigabyte. A word about FIO. FIO is an extremely usable tool, and it's extremely flexible, and it is also extremely well made by by Chris Mason, I think, one of the people working on IO in the kernel. And he's now working on a new library to make it even better be read in the kernel. And he put so many options and so many good options and given it so much thought on these options that it does the exact correct thing for the thing you ask it to do. Sounds kind of obvious. My experience is if you want to test something, then it's probably you want to mimic something that you see and let FIO do it instead of having to set up an entire environment. It is quite hard to make FIO do exactly what you are seeing and make it exactly do that. The basic thing, generate the IOs, is not a problem, but the small things around it might be not what you expect. And one of the things to point out here, for example, is invalidate 0. That's not a regular option. Invalidate 0 means do not purge the cache for the file I'm using, because what FIO does is it reasons that you want to do IO tests, so therefore if you start it, it first needs to clean the cache because it needs a clean cache situation. That wasn't obvious to me, so when I run this test, actually the second part of the test I'm going to show showed the same figure as the first one because I wanted to see the effect of caching. Didn't use this switch, so the second test invalidated the cache and did exactly the same. So I saw two of the same figures. The takeaway here is, if you're doing these FIO things, what I do is S-trace it and see if I'm getting exactly the calls that I suspect it to do. And it is painful because you get a gazillion calls, of course. S-trace is doing a system call trace of the executable. But in that way, I can validate that it does exactly what I want it to do. Because I found, like I said, I found that it does things which are really smart, but not what I expected. Okay, so now on this system, I'm going to do the following. Hopefully this is readable, not on my screen, but hopefully for you. I'm purging the cache first myself to be absolutely clear, and then I wrote a small Rust utility which simply looks into the memory. And if you look into this utility, you will see that the top one is available memory, and available memory underneath it is total memory, and the available memory is almost the entire memory. I'm not really using any memory at this point. It's a completely empty virtual machine, and I'm just fired it up, so most of it is available. Good. I'm now running my test. Now, this will take a while because it's 2 gig and my IO limits, as I explained, are not that big. So what I actually can do is travel in time and just move on, because it's a video, so I don't have to type it all. So this is what I got. But I really run this. This is the summary of this run. I run with 2,609 IOs per second and 20 megabytes per second. My limits are 125 megabytes and 3,000 IOs per second. Okay, so why didn't... Oh, another thing is, my experience is that unless there is an exception like a broken disk in your cloud vendor's environment, the limits can be reached. I take them as the limit, and I do not doubt them, because my experience is there, unless there is something really weird going on, you can always make them. That is a really important background. So why didn't I reach my bandwidth? Well, is AWS lying? But I just told you that AWS doesn't lie in here. So what is happening here? There is a third property which is important, and that's the average latency. I'm using a single process, so my single process fetches something and then returns it, and thereby there is a certain amount of time in that for doing that, and there is a figure in FIO, and that is another reason for using this page, because FIO outputs a lot of lines, which is CLAT, and that's the latency, and my average latency in microseconds is 382, which means 0.3 milliseconds per I/O. That is a really good I/O latency, by the way. If I take that time and I multiply it by my I/Os per second, I get a figure which is roughly 1 second. So in other words, despite a really low latency, I'm still bound by the latency here and not by the I/Os per second and megabytes per second limit. Now, let's perform this same test again. And like I said, I put this no validate flag in, so I know I can use the cache. And there we go. That's different. My former run, my previous run, was 100 seconds. This run is a little less than that's milliseconds, so that's less than half a millisecond. I think that's a spectacular difference. So if you need to move stuff on disk, this caching thing is really important. But what about this? My limits are 105 megabytes per second and 3000 I/Os per second. Well, I actually didn't do any I/Os. This line says I/O 0. It was all from the cache. And because it was from the cache, I'm not bound by the I/Os limit, because the I/Os limit is for going from my virtual machine to what I see as a disk, what Linux sees as a disk. So I'm not bound by these limits. And therefore, this was able to use a bandwidth of 4.5 gigabytes per second. Pure cache latency. How about 4 gig? Drop the cache, validate available memory, and then perform a retest for 4 gigabytes. Now, if you look here, I dropped the cache because I used the no validate switch. And if you look here, available memory is 3.1 gig, so that's not 4 gig. And total memory is a little less than 4 gig because the operating system needs some bootstrap memory, etc., etc. The kernel itself needs some memory. Then execute my file run, and well, let me quickly go through this, because this is taking 193 seconds, and my I/Os per second rate was actually exactly the same. I invalidated the cache, so I needed to read every single block, and because the disk is fairly consistent, it took the same latency, so my I/Os per second rate was identical. Really logical. And all the other stuff is essentially doubled. But now how about reading 4 gig? Here once again for FIO, I first did a test, and the test essentially did all physical I/Os at the same time as the first one. I looked into what FIO exactly did, and it did turn out that what the tool considered as being correct is keeping a map of every block and very exactly, randomly read every block of the designated block size and read them, which meant that it effectively pushed out, because I have too little memory to store all the data, it effectively pushed out all the other ones, so I did all physical IOs. By adding no random map, I think I replicate what a normal application would do, and then truly randomly and sometimes hit the same pages multiple times. So no random map. And then I got this figure. And this still takes a long time, because as soon as you have an active data set, which is, and an active data set is the amount of data that you try to query, which is bigger than your cache, which is, so you have a bigger active set, then your cache effectivity plunges. And that is what this shows you. This is still an enormous amount of time, because I've done roughly of the total of 500,000 IOs, I did 330 IOs. In other words, outside of understanding these memory things, if your data set starts to grow and it outgrows the amount of memory which is available for caching, then it will not gradually go down. A lot of people have this idea that if you start to oversubscribe, that it will slowly deteriorate. Sometimes it does. In IT technology, what I mostly saw is what a friend of mine, Carrie Millsap, described as the hockey stick, and that is, if you have enough resources and you're not using all the resources and you start pushing it, for example, a small data set in a big cache, and you increase it, performance stays consistent instead of going up, because it can cache it all, so it's good. It's only once you go beyond what is available and it needs to drop things from the cache in order to fill it with new ones. At that point in time, your performance will drop significantly, and hence the hockey stick, it goes, and then it goes all of a sudden up. And I'm convinced a lot of you saw that. Instead of what you expect to get slowly worse, one day it's great, and another day it's total hell and total misery for an application, and everybody is complaining. And that is why, as soon as you have a bigger active data set, the likelihood of pushing out this stuff and filling it with new stuff, essentially a big circle of doing IOs and caching, that's what is happening. And you can perfectly see it here and replay it for yourself if you like with these options. I have a cache of 3 gig, an active data set of 4 gig, and my performance dropped tremendously. But is this reality? This tiny amount is not realistic. If I'm using data 9 out of 10 times, there is an actual application running on the system, and that application needs memory, because that is why you fetch data to put it in your application. So how would it look like if there is an actual application running? And for that sake, I created this tool, Eat Memory, which I described previously. And with Eat Memory, it's a really simple Rust application. What I do is I simply create a vector, so an array essentially, and I fill it with zeros, which means that I'm paging in the memory. And allocation doesn't do anything. Linux lies to you if it allocates something. What it matters is once you start using that data, Linux at the very last moment will page it in, which is called a page fault. It will realize that memory isn't actually there, and then it puts the memory in your in the process space of your memory. That then is called resident set size, so that's the RSS statistic, and puts it in, and that's what this utility does. So it isn't a smart utility, it's a small utility, and I'm doing a really stupid simple thing, create an array for which I understand exactly how much it will allocate. And in this case, I'm using 2000, so of my 4 gig, I'm allocating 2 gig with this tool. And now I think, and this is the important part, I think, is what I'm now doing is I'm repeating the exact same test for the 2 gig file. But with memory allocated as if an application is running on this system. And if you now look at available memory, you see that the figure is way less. It's 1,135, so 1.1 gig roughly. And you can see that used memory is over 2 gig. So that is, so this simple utility allocated the memory. And now run the same test. Now, luckily I can transport you forward in time. Now I'm doing 98 seconds. So, oh sorry, the first run obviously, I invalidated the guess. So the first run is identical because I did not have any of these pages and I read them. So it needs to be the same. So this time is roughly equal, and because it's bound by my I/O latency doing physical I/O, where there was no change here. The change is, and I added no random map to simply just give it a little positivity, because otherwise I would get the same figure. So I added no random map, run the test again, and by running the test I get this huge difference. And this is, it's IOs per second is a little above the limit. Why? That's because no random map allowed me to read some things from the cache, and that is included in the IOs per second figure, but not a large, because once again this is the hockey stick theory. Because my active dataset is 2 gig and my available memory was 1.1 gig, I had a shortage. I could not cache this entire set in memory, so therefore it does all the IOs. And in the last line, reason physical I/O had to be performed. I'm doing 192,000 IOs roughly. So, but the important part here is by changing memory allocation, and this is the really and this is the thing which I see which people find hard to understand. By doing this memory allocation and doing a test which is exactly the same as my previous test, my response time difference for a cache is going from 0.4 second up to 74 second. This is actually one of the phenomena that I see happen a lot, where people are confused, saying we tested it and now all of a sudden it didn't work. Well, what I said previously, if you test it on a server with the application not running, so it has all the memory available, and you did run your tests of doing I/O, it's good. If you start your application, and maybe even if the application is started, it will not have paged in all the memory, it might be still reasonably good. And then if your application runs and allocates all this memory, and then your I/O is all of a sudden is really bad, this is your reason. Now, writes, and I have to speed up a bit here, but writes are special, and the reason writes are special, well, let's look at this run first. A 2 gig run on a server with no memory taken. So I'm doing the same thing. We'll see the same figures. And with a 2 gig write, I'm not getting the same figures as a 2 gig read. This is really, really important. I still get a great figure, but with a 2 gig write, I get 61,000 writes, IO physical writes, and my IOs per second is great, but I'm not getting the same figure as for reads. And like I said, writes are special, and this is something, do not compare reads with writes. A write by a process, unlike popular belief, and this is another thing which, if you remember this, this can really help you a lot. A write in Linux, a buffered write, only dirties a buffer, and then it's done. A write in Linux, a buffered write, does not perform anything physical. The buffer is dirtied and a kernel writer thread performs the write for you. And because and a write cannot be discarded like a read, a read buffer, which is does not have any processes attached, can be ditched at any time, no problem. If you need it again, you read it again. A write can never be discarded at will. A write has to be written before the buffer can be freed. Because of that property, the kernel has a few limits, which are generally at something like, I didn't put the ratio in, but it's something like 15%. And there is a myth on the internet and in a lot of documentation, or not a kernel documentation, but a lot of blogs, that these ratios are from total memory, which is also not true. These ratios are for available memory. In other words, if you allocate a lot of memory, your available memory will get less, so your ratio of writes which are allowed to exist there in the first place diminishes really quickly by allocating a lot of memory. So that is a really dynamic way of working, and that is really important because I can hardly find any blog who describes that it actually is true. If you take this presentation, and my Twitter handle is @Frits Hoogland, so you can also ask me if it isn't available, but I will make it available. Then this link also shows you even the lines in the kernel where it will tell you to do so. So how does that work? Well, this is really interesting. A write writes, and inside the write call, the kernel evaluates how much I/O pressure is being done, and based upon that I/O pressure, it will hold a write for a bit. The bad thing is you get the impression that it's actually doing the write and waiting for the I/O to happen. Instead, what it is doing, it simply throttles your process in order to overcome the problem of getting too many dirty pages, because that's the intention. And this is called balancing, but it is simply halted for a bit by the kernel for the sake of that. So, and this is so unlike what a lot of people think is actually happening. This is the factual thing happening. Well, can I make it fast? Well, yes, of course. If you make the amount of writes that you do fit within the ratio within available memory, you can make it fast. So let's test with 500 megabytes. And with 500 megabytes, the amount is low enough, so my amount of IOs which I'm actually performing is 0. I'm not within the ratio, so it allows all the buffers to be dirtied by the write. I'm not doing any IOs, and all of a sudden it's fast again. And hopefully, and I have only 5 minutes left, so I realize that I should have done lesser talking in the beginning, but hopefully it painted this picture of how this works. You can get these drastic changes of I/O, which is really fast because it's buffered, because it fits. And then if for whatever reason, whether your amount of IOs is too big to fit within available memory, or in the other side, if your amount of IOs is the same, but the memory allocation of the system overall was increased and therefore available memory decreased, it could mean that your same IOs now all of a sudden are really slow. And there is no gradual decline. It's either it's really nice and cached and fast, and if it has run out of it, then it's probably very slow and misery, and it's really peaky in that sense. And that is what I see a lot from doing also in my past, doing consulting on I/O problems, that people are having problems controlling this and not understanding why this is so seemingly random. And that is the purpose of this talk, to show you these are the mechanisms. Reads are not writes. And writes, there is a perfectly well way of measuring and seeing it, but you have to understand these mechanisms. And again, that is the talk of this presentation. And I've got the same reality slides here, you know. And what the reality one is once again allocating memory. and then doing the same, and because I lowered the amount of available memory, therefore the cacheability, the performance will be bad. So that's the purpose of these. So the conclusions. You are probably using buffered I/O. Keep track of available memory. That is the key statistic, which tells you that the memory which is available for taking if you are doing this. And therefore, available memory is roughly what is available for cache. And regular allocations. Don't forget, you are perfectly normally competing with regular allocations of applications. Reads and writes are different. Reads can just fit in available memory, essentially, and writes need to fit within this dirty ratio, which, from the top of my mind, is 15%. Therefore, if you're doing I/O, and this is a hard part, this is not easy, I understand that, but if you understand your active data set, so the amount of data which you are working with on reading and writing, that really helps, because that is what you can combine with available memory to see if it fits. My tests were performed without swap. Most systems have swap, and I'm not, and my company uses VMs which do not have swap, and both are okay. I'm not really sure. If you add swap, on one hand, it allows you to have kind of a safety net for allocations because it can push out stuff. It has really interesting other properties, like if you are using your cached, if you are using a file cached and touching these blocks, they become higher prioritized on the kernel LRU list, least recently used list. If you have pages for an executable which are only used during startup, so bootstrap code for your application, these pages will have a single touch, which means that if your IOs get a bit higher and they need memory, then the kernel will start paging, and it will page out these blocks of bootstrap code because they only had one touch, so they are lower on priority than things in the cache, which means these get paged out. This leads and still is leading to a lot of confusion that people think they have too little memory. Yes, you did have too little memory at a certain point in time, based upon the logic of a touch count. And is it a problem? Absolutely not. That page is bootstrap code. It will never be read again in the lifetime of that application. So it is not an issue. There is lots what I can say about that you also should not strive for getting these out of swap, because it's never used again. Perfectly in swap. No, but that is another discussion. So swap is okay, but it makes it a little harder because you then have a second stage of memory which is there, which has properties and which adds to the picture, making it a little more complicated. So that is the last part, and then I'm exactly done with 1 minute left. Are there any questions or remarks? Did you recognize some of these things that I said with applications and the peaky behavior of I/O? Um, if I translate it, please say me if I translate it correctly. So translate if I interpret it correctly. You're saying we're using Kubernetes, and if I add swap, is it a problem, or even better to add a little swap to a? I would say that, especially if it's just a little, swap is not mandatory. It's kind of this knee-jerk reaction of a lot of admins to have this desire, because swap was always there to have swap. I was hesitant when I started working with Yugabyte and saw our virtual machines without swap. I was hesitant and said we probably should have swap. It is perfectly fine to run without. There is only one downside. If you are running into over allocation of memory with swap, you have kind of this this protection mechanism, which essentially is kind of a soft cushion where you run into, where things start becoming slow because you get this massive traversal. We've all seen that, right? Swap in, swap out, this massive traversal in and out from swap. And if you allocate beyond that, your system will start out of memory killing, because that's what's happening. If you don't have swap, you don't have this cushion for your crash. Instead, it will start doing out of memory killing earlier. The question you have to ask yourself is it useful to have this moment of degraded performance where I'm doing swap in, swap out? I am starting to lean towards thinking, if I can control my VM, and especially in Kubernetes, you know, if that's meant to be a single purpose, a pod with running a single application for a single purpose, if I can control that and understand what it does, then I would bias towards, no, don't use swap. It's a complication, and you're not getting any good of it. You get this cushion, but hitting the cushion meant you were still already falling, and you should strive for not falling, not for getting less sore, hopefully, if you do. So it's kind of a long answer, but I hope it gave some pointers.